When a metallic surface is illuminated with the radiation of wavelength lambda, the stopping potential is V. If the same surface is illuminated with the radiation of wavelength 2 lambda, the stopping potential is V upon 4. The threshold wavelength for the metallic surface is 4 options here. Let us find the right one. The general equation is very simple. So h nu equals h nu naught plus half m V max square. That half m V max square is replaced by EV naught. So let us write this equation in terms of EV naught. EV naught equals h nu minus h nu naught. The nu frequency is replaced by C upon lambda. So we get a new equation apt to our problem. EV naught equals hc upon lambda minus hc upon lambda naught. So let us go with the first radiation. For the first radiation, the stopping potential is V for a given wavelength lambda. So EV equals hc upon lambda minus hc upon lambda naught. Let us go for the second radiation. For that, the stopping potential is V upon 4 for a given wavelength 2 lambda. So the new equation is EV upon 4 equals hc upon 2 lambda minus hc upon lambda naught. Let us substitute the value of EV from the first radiation. So we get 1 upon 4 multiplies hc upon lambda minus hc upon lambda naught equals hc upon 2 lambda minus hc upon lambda naught. The 4 on the left hand side goes and multiplies the right hand side. So we get hc upon lambda minus hc upon lambda naught equals 2 times hc upon lambda minus 4 times hc upon lambda naught. So the minus 4 hc upon lambda naught is on the right hand side. On the left hand side, you have minus hc upon lambda naught. So we get 3 times hc upon lambda naught, that will be equal to 1 time hc upon lambda. Hc upon lambda on either side get cancels. So we get 3 lambda equals lambda naught. So the threshold wavelength equals 3 times lambda. Option C is correct.